2、1。
Hi everyone, today I'm excited to share our project, Improving DQN Network for Atari 2600 Games. The group 151, our group members are Chen Zhang, Yifan Jing, and Mao Huang. Our motivation and problem. Learning to play Atari 2600 games directly from raw pixels is a classic and challenging path in deep reinforcement learning. The original DQ network or DQN showed that a CN could learn game strategies from images and even outperform humans in some games, but it still has some limitations. One key issue is use of frame stacking and frame skipping. The agent only see every K frame and stacks the last four to understand motion. This saves computation, but it also means the agent might miss fast events like flashing lasers in Space Invaders and fail to react in time. So in our project, we first reproduced the original DeepQ network, then explored ways to improve it through architecture changes and hyperparameter tuning, aiming for higher scores and faster convergence. Let's talk about why neural networks are useful and where they fall short. Strengths: learn end-to-end from raw data, no handcrafted features needed, and make data-driven decisions using replay and updates. And third, work across many tasks, showing good generalization. Limitations: that need a lot of data, which can be hard to collect in real-world tasks. And models trained in simulations often don't transfer well to the real world. Also, training can be sometimes unstable. Our baseline and improved DeepQ network. Our baseline and improved models both take in 4 stacked frames, size 84 plus 84. We use TensorFlow 1 in graph model for implementation. The improved version keeps the same input structure, but adjusts the architecture and training settings to better handle skipped frames. Here's our network structure. So first, layer 1 is a convolutional layer, is 8 times 8 filters, straightforward. And there are layer 2 is also convolutional, also 4 times 4 filters. So the remains are shown here. And the output layer 1 output per possible action is the representing each action's Q value. And this setup allows the model to learn spatial and temporal patterns from input frames. Thank you, Michelle.
开始。
We followed standard Q learning method. Each input is made of 4 consecutive frames. The target Q value is calculated as shown in below this formula. And we will use MSE loss between predicted and target Q values. So we also use RMS probe optimizer, and the model supports checkpointing, so we can save and reload training process. Evaluation and performance. We track several metrics to monitor training. The first is training loss and also global setup, step count, convergence, stability, and Q value prediction. In future work, we plan to test our model in more games and environments to evaluate how well it generalizes. Environment setup and data. The emulator loads games, RMs, runs the game, accepts actions and return rewards and images. The dataset module stores transitions like states, action, reward, and next state, and allows efficient sampling for training. Here's our overall framework. Here's how our system works. There are 4 parts of it. Parameter module, emulator module, dataset module, and DeepQ network module. This is the result of our experiment. You can see here the improved version of average Q is better than the baseline. And the improved version of model, it reaches a higher reward also. The reward is also calculated as average. So we can say that our tuning has been effective, it has been in effect with these games. Prior our work, our three group members, we all have some prior works. Nonghua have previously worked on computer vision tasks, and Chen Zhang have previously worked on optimizing UAV cooperation and target finding using multi-agent reinforcement. Yifan Jing have compared 5 CN algorithms to develop machine learning model. This is our references. Thank you.